Hello and welcome back to Educator.com and welcome back to physical chemistry. So today we're going to start our discussion of the hydrogen atom. Now we're ready to put everything together and we're ready to talk about the orbitals, the energy levels of the hydrogen atom. So one little bit of warning before we start here. This is going to consist of multiple lessons and it's going to be very heavily mathematical, at least in the sense of all of the symbols floating around on the page. Now, ultimately, what's important is we want to be able to find the solutions for C, the wave function for the electron that's moving around the proton in the hydrogen atom. So that's what's most important. It's easy to lose our way. I'm going to present it in a normal fashion. I'm going to present most of the mathematics, not all of it. But it's really, really important that you separate, don't get intimidated and, just alienated from all of the symbols on the page. I'll try to keep it clear as to what's important and what is just cultural information, what is just part of your scientific literacy. I could just present the solutions and say this is what it is and then launch into some problems. But we also want you to understand where it is that these things come from, because that's where real understanding takes place. So ultimately, you're only responsible for the solutions, but we want to show you where these solutions come from and why they take the form they take. So just a little bit of warning, so don't be intimidated. It's just symbols. Okay, let's get started. So in discussing the rigid rotator, we held R constant. Discussing the rigid rotator, we held R, the radius of the turn, constant. And we allowed theta and phi to vary. So again, something rotating this way, basically just something spinning around some fixed center. And you had the theta, which is this way, and the phi, which is this way. So those are the things that varied. So it gave you all of the points on a sphere. Now we're going to allow R to actually change. So now we're going to allow not just movement on a sphere, but we're going to allow it to be close, we're going to allow it to be far. So all of space is going to be considered now. Now we allow R to vary also. Excuse me. Now for the hydrogen atom, we take as our model a fixed proton in the center, a fixed proton at the origin, so that'll be our zero position, our origin position, and an electron of mass m sub e interacting with that proton, via the Coulombic potential. So basically, this is just a fancy way of saying we have a positive charge and a negative charge, and they're going to interact with each other based on the fact that positive and negative charge attract each other. That's it. That's all we're saying. And the Coulombic potential is, so the potential energy, one charge of a positive charge and a negative charge, the distance between them being R. So the potential energy is going to equal minus E squared over 4 pi epsilon sub 0 R. Now, E here, it is the charge on one proton, or the charge on an electron in coulombs. So it's going to be 1.602 times 10 to the negative 19 coulombs. And this epsilon sub 0, that is the permittivity of free space, and its value is 8.854 times 10 to the negative 12th. I never memorized these. C squared over joule meters, or per joule meters. and it's called, as I said, called the permittivity of free space. Permittivity of free space. Okay, and r is the distance between the proton and the electron. So is the distance between the proton and the electron. So basically you just have this proton here in the center, and you have, you've got this, you already know this already, electron that's moving around all over. Not necessarily in circular orbits, but now it's moving around this way, it's getting close, it's getting far, it can be anywhere. Okay, so let's see what we've got. Now, so basically we dealt with this rigid rotator, which is a perfect sphere, and then all we've really done is now allow the electron to move in and out, get close to the proton, get far from the proton. So we still want to work in spherical coordinates because the symmetry of the situation naturally lends itself to spherical coordinates. That's why these various coordinate systems exist, because certain problems lend themselves to a particular coordinate system, so the math actually becomes easier. Okay, so in spherical coordinates, you know what, let me go ahead and erase this. Let me see, should I go ahead and put it on this page? Well, that's fine. So the spherical, I'll write it here. Now, so the spherical symmetry of the model compels us to use spherical coordinates. And what we're going to end up with is something like this. So the Schrödinger equation is going to be h of psi. Now psi is a function of three variables, r, theta, and phi. R, theta, and phi is equal to E times psi of r, theta, and phi. The eigenfunction, eigenvalue representation of the Schrödinger equation. That's it. And h is going to be, the Hamiltonian operator here is going to be minus h bar squared over 2 times the mass of the electron, del squared, minus the potential energy. The potential energy was the Coulombic potential here, minus the E squared over the 4 pi epsilon and r. Okay, now let's go ahead and so we know what del squared looks like in Cartesian coordinates. So in spherical coordinates, it looks like this. So let me go ahead and rewrite this. So h